Good evening, sir.
Today we are revising the chapters we have done. I'll send you this file. We'll check this out. We have given some data. This is normally useful for the bone neighbor cycle. No? Bone neighbor cycle part also there. Some hydration one also there. No, hydration one, no, not bone neighbor. Electron affinities are not there, so hydration. If you remember, okay, now they are saying you are disconnected. That one to join again. Share the paper. Chanu, did you get the paper? Get the paper. Okay, now I'm sending it again. Okay. We are revising the chapters we have done for the moment. Now they are saying complete the energy cycle involve interchange of solution lattice energy, and other one is hydration. Other one is the hydration enthalpy. Now this is not the format we are used to. So examiners can change it. So we used to this now. We are used to this format. But not that one. Not that one. We are used to.
Sir, normally, like if you take it upside down, of course, that way.
No, not hydration enthalpy. We are not used to that, no. But we did in the class. Those are normal Hesper diagrams. No? Yes, that's what. Now, examiner is given the Hesper diagram. Look at the book. Hydration enthalpy. We are used to this. No? You remember this. You have
Understood, sir. The upper one and the lower one.
sodium chloride solid. Then I can dissolve it. I can dissolve it straight away. Then I can get sodium chloride aqueous solution. Then this one we say, if I mark it that way, this way actually lattice energy. No? This way is the lattice energy. I'll be getting sodium plus gaseous ions, chloride minus gaseous ions. This is the
Sir, that's atomization, isn't it?
there's no atomization here. That's what you are mixing it up. This is not the bond neighbor cycle. This is the lattice energy cycle. There are two we did. This is not the bond neighbor. That's why. After some time, you start forgetting. Yeah. We'll clear it up. The reason today we are doing either way, we are doing both. Huh? Yes, I just want to.
So lattice energy normally is Na plus gaseous to Cl minus gaseous to from
This is correct.
NaCl solid.
That is correct. Na plus to Cl minus to this lattice energy.
Understood, sir.
You
Okay.
are talking about the bond neighbor cycle. This is the, you know, what is this? This is the enthalpy of hydration. Hydration. This is the enthalpy of the solution. Right, the full word hydration. Okay. This is the chart we are used to. Copy that. So now in this one, we know if I say this is equal to this plus that. If I go into this into this plus that. So for example, enthalpy of hydration. In a book right under we did this earlier. We have forgotten it. Is equal to
Sir, 1 mole of gaseous ions become aqueous ions.
correct. Solution.
Maybe, sir, we write it like X plus gaseous plus AQ to form X plus AQ.
Yeah, correct. So now copy that. This is what we are used to now. Now examine is twist in this.
Sir,
Yes,
so can we write the LE arrow upward and right minus LE?
correct, correct. That's we did that earlier also.
Yes, sir. I can remember it like that.
That's correct. Yeah, that's also correct. We did it earlier. Both ways we did it. So if you put it that way, it will be minus L. Yes.
Yes, sir. Yeah.
Okay.
So should we write that down?
Yeah, copy that down. No, you have forgotten this. No, that this one you had to buy heart. This is the standard one. Now examiner is changing that into a Heslu cycle. This is standard.
So the topic is revision.
A revision, yes. Today we are doing revision of the chapters what we have done. Born-Haber, mainly Born-Haber cycle and this and rate of reaction. So we did Born-Haber cycle, this and rate of reactions. Order of reaction, those stuff. You have to finish copying the thumbs up. Now this part you have to buy out. Huh? Then now you stick to one model. Now this is the most common model. Textbooks also have this model. Other one is you can write this, but the negative you can write it that way, and you can say minus LE. That's also okay. Let's stick to one model. Then we can manipulate it. So copy that and give a thumbs up.
So is it fine if that arrow touches that lower line of all this stuff?
So what? Show it in the screen. What you're telling? Yes, you touch the line. That's correct. They won't check it that one. You touch the lines. That's correct. There can't be gaps though.
Done, sir.
Done. Others done. Okay, now this one, examiner can change it any way he like. Now, for example, you put this into one box. As I tell you, you put this into one box. You put this into another box. Now you stick to your box. Now the reason is now when they give sunlight that you draw this in a corner. You draw this in a corner and fit it. Now you put it in this box. Now I can manipulate these boxes the way I like. Now, for example, I can put the green. If I put the green color box here, red color box here. If I put the blue color box here, I can connect them. I can connect them. Okay. It does not have to have layers. Now, this is like the enthalpy level diagram. Now, this is the diagram. Now, for example, if I go from red to green, I know it's lattice. Red to green, lattice. Green to blue, it will be the enthalpy of the solution. If I'm going red to blue, it will be what? Enthalpy of the hydration. Now I can switch the boxes anyway I like. I'll go for another diagram. I'll go the red one here. Then I'll go the blue one here. Then I'll go the green one there. You should have three colors. Use three colors. It's better. Now if I go from this red to blue, I know this one. Enthalpy of hydration. Red to green, it will be lattice energy. Then we say blue to green. Blue to green is minus enthalpy of solution, but normally we go from green to blue. Green to blue. If it is opposite direction, okay, now if you have colors, use colors and draw these two. So can you say examiner can change it anything, anyway, he likes.
So,
Yes,
so if someone decides to go like now if we did go this way, then of course this will become minus
minus
enthalpy.
enthalpy of ideas. That's what you remember. Now, the easiest things to remember is this because this is the standard and any textbook have this model. The examiners can just, so you remember one, using one, you can get all the others. You stick to one, this one. We stick to this. But when the examiner change it, we can get anything we like.
So it has to be delta H here, is it, sir?
No, the delta H height. Normally, this hydration will be delta H. H is missing. No, correct. Delta H hydration. Delta H. Then you must have hydration. The height, we normally write HID on. This also we write SOL only, but I wrote the full thing. Okay, this is delta H, then HID. I remember. What of it? So the afternoon should come with him. So, those colors if you can.
So done, sir.
We're done. And now we'll go back to the question and we'll see. Now, yeah, complete this setup any way you like, based on the earlier one. We have
So we
KCL.
have to fill this, is it, sir?
Other two boxes, yes, I do it on screen here. Other two boxes you can fill any way you like. Now fill the two boxes. How you are doing drawing that too, so they are okay.
Yes, sir, I am drawing this to identify.
To figure it out. There you have the KCL solid, yes. The K plus C minus C. Yes. The one is KCL latest. That's what we know. Based on that one, we had filled this. When you're filling this, use their notation, not like this delta H like this. Okay. Now we have to put the arrows. Now these two boxes you can change any way you like. It's your choice. Okay. KCL, okay. Yes, that's KCL data. If you put the arrow that way, you have to write a minus. It's okay. Put the notations. That is, yeah, their notation we have used. They say delta H LATT. No? If they are notation, that's correct. The other one is from KCl solid to AQ. Delta H solution. Then the next one is you had gone KCl, that is minus delta H hydration. Is the way he had used arrows, he had used it like that. If he had put the arrow other way around, he can say plus delta H hydration. This is fine. He reversed it. Of this down. So this method,
I wrote minus bracket delta H
it's
hydration
okay.
bracket
It's okay.
plus.
With the minus or without the minus, it's fine. Well, minus should be there with the bracket or without bracket. So this is the base. We memorize this because we can't memorize all the possibilities. No, we memorize one possibility. From that, we can get the others. Or copy that.
So can I calculate the answer? Yeah.
I think the next part we had to calculate the amount. So just copy it here. I think next part we had to calculate the. Either it's there. Yeah, yeah. No, there's not for this. They're asking for magnesium and something. No, not for this. They didn't ask. They asked enthalpy. Did they ask it? Complete the initial enthalpy solution. And that is
No,
an
sir, no, sir. They
no,
want me to fill that.
something. They're asking for MgCl2. We had to do that. Looking at this one they ask in the diagram. Next one without the diagram, they're asking you to get the value. So we can use the equation straight away.
Understood, sir.
So copy this. Next one they have given a magnesium chloride. So that is
So the up ions must be gaseous state. Is it, sir?
yes, yes, one.
The upper ions. Yeah,
That,
so it has
yeah,
to be
this is
gaseous,
correct.
is it, sir?
That's correct. Yes, yes.
Not aqueous, is it, sir? The ions normally.
No, no, I am Acres here. If you want, you can write this as Acres. Wait, wait. Sure. If you want to write Acres, this one you can they can write Acres. There's another way of writing this. Huh? This one, not this one. That is gaseous. But
Yes,
this
sir.
one,
Na plus plus Cl minus
yeah, this
AQ.
one you can write if you want. That's how we know NaCl Acres. I can write like Na plus Acres as well as what Cl minus Acres. We know that from all the sodium
So
chloride.
the upper,
Upper one gaseous.
I'm sorry.
Okay, after finish copying the terms.
The minus one, we don't need to put brackets and write. Is it, sir? We can just say write minus delta H hydration.
Yes, but normally what we do is we put the arrow other way around and try delta H, it's fine.
So the answer will be the same. Is it, sir?
Same, 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 same. Okay, after finish copying the thumbs up,
Done, sir.
done, no? Others done.
Yes.
Sanu can listen done. I didn't see the okay, done. Done. Sanu done. Okay, then we'll go to the next one. What are they telling? Use the table to calculate enthalpy change of hydration of magnesium ion. That's mean they gave the hydration of the chloride ion, not the magnesium ion. It's like this. When we write this equation, we get this hydration. So this hydration is hydration of sodium plus hydration of chloride. This hydration. Both should be hydration. This gaseous state, 1 mole plus dissolved in the aqueous solution. So therefore, this hydration means both hydration. So what we can do is we can rewrite this equation. This is standard equation. We can rewrite this equation. Then in the place of enthalpy of hydration, they did not give me the magnesium hydration, but they gave me the chloride hydration. Now, where you wrote this also will write there. Now, this one hydration mean actually this hydration will break into two. That is what delta H hydration of Na plus delta H hydration of Cl minus. Both hydrations are there is equal to lattice
Sir,
energy plus delta H solution. Solution. Yes,
excuse me, sir.
here.
So then we can use the delta hydration value and subtract it by the chloride one, so we get the sodium, sorry,
Okay.
magnesium one.
We can write the equation like that. Or we can write the equation like this. No, we can write the equation like that and work it out here. Okay, first copy this below what you wrote there. Now this hydration mean actually hydration of sodium plus the hydration of chloride separately. Sodium plus ion and chloride ion separately.
This is for which sum, sir?
Now earlier example we wrote in the book. No?
Okay.
Then
Yeah, okay.
the book we can copy it here.
So under that, is it, sir?
Under that copy. This sum is little tricky because it's magnesium chloride, so there's twice hydration of chloride ion here. In the I'm telling the sum we are doing.
So the delta H hydration Na plus must be like a power, or it must be like
Plus mean charge plus.
also like the whole iron, it's written smaller to the delta H hydration
No,
notation.
these are notation. This is my notation. The examiner can use. Did you see now? I just wrote lattice LD. Books also sometimes write LD. But this examiner use something like this. No? So these notations can change slightly from the examiner book to book. He wrote something like this. Let E also you put it. No, something like that. So these are notations. Huh? When you see the notation, you must be able to understand that. So examiner
Understood, sir.
can figure out what you are writing. That's enough. Because we can't write the full thing. That's why I wrote here solution. But someone can write SOL. Someone can write the full solution. SOLU also, if someone write, that's fine. Yeah. We see that he's using a notation for this. So his table has some notation. We'll see what that notation is. Okay, done. No, this one. Then we'll go back here. This he is a hydride of chloride. And he's writing right there. Okay, then now we'll write the formula. What's the formula? We'll write the formula. That what we have is hydration is equal to that is energy plus the solution. If you want, we can write in show also, yeah. Not without big notation also. If you write, that's fine. Dehydration. Yeah, we can use that. Yes, our notation. Now here, one hydration is missing. No, we'll go and pick the values. First, the value of lattice energy value is given. That we'll put it. For magnesium chloride, we are doing yes, correct. Then the solution value also given minus 151. When it comes to the hydration, magnesium hydration is not given, but chloride hydration is given. Hydration side, I can put the magnesium hydration plus twice the chloride hydration because this is magnesium chloride, 2Cl minus should dissolve. Okay, 364 into 2. 2 plus, yeah, that's what we had to find. The unknown. That's x only we had to find. That's correct.
So,
Yes, correct.
so the lattice energy values, I put it in bracket. Is it fine? So I didn't change the sign also. I just put
No,
-2492 and put it in
basically,
bracket.
the way you had it, the equation is correct. Now simplify. That's correct.
So normally in the slow ones, we normally the like the sign changes. It's according to arrow direction. Here we don't have to think about that.
Here also same. Yeah, his
So we
lower.
can just take this and put it here with the brackets
That's the
also.
standard. No, this is lattice energy, not minus lattice. They'll give lattice energy always.
Understood.
Okay. So lattice energy is always exothermic. It's minus. Correct. That answer is correct. Copy that.
So we can
Yes. Yeah, correct.
so we can use the unit which I told you. I didn't write kilojoules. That mole to the power minus 100/1.
Same way. Can write both. Now finish calling your thumbs up.
Done, sir.
Then go next one. Then they are asking, okay, the part. Explain the reason why the lattice energy of magnesium flow is more external than lattice energy of KCl. Remember it like this. Your O-level typical question, but now this is the modified version. Now, O-level will be telling, do you remember O-level will be telling why magnesium chloride ionic bond is much more strong than potassium chloride ionic bond? What might be the reasons?
What to what say? Magnesium chloride to
Magnesium chloride ionic bond is stronger than, okay, now can you say magnesium chloride is more exothermic than KCl mean? In other words, see, magnesium chloride is minus 155. What was the, it's not minus, but lattice energy of minus 2493, whereas lattice energy of KCl is minus 700. They are referring to this. So this is the lattice energy mean like the bond enthalpy. There is no bond, no, there are no covalent bonds here. This is similar. That is now in O level we did this in a different way. We were explaining magnesium
Charge density.
chloride ionic bond is stronger than, it's the same thing, same stuff. KCl ionic bond. Magnesium chloride ionic bond is stronger than KCl ionic bond. Magnesium chloride ionic bond is stronger than KCl ionic bond. So what are the reasons for that? Why this ionic bond is stronger?
The magnesium chloride, the magnesium cation is slightly smaller than potassium. So the charge
Yes,
density
correct.
is
One is magnesium 2 has a smaller cation than potassium plus. Yeah, that's correct. What's the other one?
the higher charge and hence this higher charge density.
Correct. But higher charge density due to small as well as charge. Magnesium is 2 plus charge. Potassium is what? 1 plus charge.
+1.
Yeah, plus 1 charge. So charge also more, radius also less. Therefore, yeah, charge density is high.
Charge density.
Therefore, there will be what? Greater attraction between the magnesium 2 plus and chloride minus ion. So it's the same question what they had asked in the O level, but now we use big words. Okay, did you get it? We are telling that is energy. That's correct. It's stronger. More exothermic mean bond making will release energy. So bond is stronger. That's why while make the bonds, it will release more energy. Bond is stronger. Okay. So that will be the answer. The right answer. Okay. Oh, I'll straight away show the answer on the mark screen. So you don't have to buy heart. You already had buy heart at this. Can you see? I'm showing it. The mask scheme now. This is A-level mask scheme. See, it's similar to the O-level thing. No? Copy that. So when they ask this question, that exact O-level answer will score you the mark.
So,
Yes. They don't
so
tell charge
is it
density is 5.
necessary?
That's all. Huh? Yeah.
So normally we always say about the thermal decomposition, like when polarization increases, when the cation also becomes smaller with a higher charge.
So there's a greater charge only. The charge density was not given by this examiner, but you can write the charge density. It's correct.
So like in
Yeah.
polarization, like polarization, the part where
No,
the
that's something else.
covalent character,
That we'll talk about that later. What you are telling is the theoretical value and the real experimental value.
just it was then is like these
Yeah,
two parts are quite
okay, that's also
confusing then.
that's yeah, that I mean there's a character of covalent. No, that's another thing. Yes. Yeah, this is like the O-level version. No? Here we are not talking about the covalent character because this is ionic bond with a covalent character. Again, I'll repeat. Now, when they ask this question, they use the word exothermic only. They say the bond lattice energy is more exothermic. In O-level question, they say what? Lattice is stronger. Can you see the difference? O-level lattice is stronger is replacing A-level. Lattice energy is more exothermic. That's the only difference. Did you notice it? The question difference. Answer is almost the same. Answer is
Yes, yeah. Well, that means because lattice is much more stronger,
yeah,
more exothermic means more release of heat energy to the
correct.
surrounding from the system.
Correct. Yeah. So copy that. Now finish coming with thumbs up. So somewhere, if you want, you can make a note. This question is the O-level question is magnesium chloride is a stronger ionic bond than potassium chloride. Explain why. That's the O-level question.
Yeah, I wrote answer. I wrote Mg2 plus is smaller than K plus and Mg2 plus is greater in terms of charge than K plus. Hence, between Mg2 plus and Cl minus, there will be greater attraction.
Fine. Yeah. Very This
So should we talk about the ratio also? Like Mg2 plus 1 and the Cl2 minus Cl minus only 2 ions are there?
no need. This fine. You can that extra thing what you mention can mention is Mg2 plus have a higher charge density than K plus, but this is implied here. No? These two combined together, that is it's showing higher charge density. You can write it separately as well. After copying that, give a thumbs up. We'll move next one.
Done, sir.
Done. Others done? Done. Done. Shanuka done? Okay. Go to next one. Okay, now these things you have to buy heart. There is no other way. Okay, right on. Then there is enthalpy change of atomization. Right? What you remember?
So it's standard enthalpy change of atomization.
Yes, standard enthalpy of atom. Yes, correct. It's what in needed form 1 mole of gaseous atoms from the element in its standard state. Element in its standard state at standard temperature and pressure. Enthalpy change when 1 mole of gaseous atom form from elements in its standard state in a standard temperature and pressure. So at 298, if you say at 298 also fine. You have to buy heart. Now standard state at 298 mean standard 209, this is room temperature and pressure. 290 RT, you know. Say that RT, room temperature and pressure. Say it like that, stay at 298, no? In standard state at 298, right? And the formation enthalpy change obtained under standard conditions plus gaseous atoms formed from 1 mole of the substance. So 1 mole of the substance. Okay, fine. Correct. No, rather than substance, element is better, no? Because they had highlighted element in this mask.
So I put in brackets standard state of element.
Element, you said the inside bracket. Now, fine, sir. That's it.
So I wrote standard state of element.
Standard state, but this is room temp standard state of element. That's also fine. Yes, but they are putting it inside the bracket, standard state at 290.
That's 290 Kelvin and
That's room
101
temperature.
kilopascals.
That's not the standard temp, that's room temperature, you know. Okay, no, did you copy? Done.
Done.
Okay, we'll go next question. What are there? These things you have to buy out. There is no other way. Then they're asking the first electron affinity. They're asking first
So
electron.
it's the opposite of ionization in
Correct. Yeah, enthalpy change when every atom in 1 mole of gaseous atom gain 1 electron. But the second one is easy, you know. Enthalpy change when, this is second one is B. Enthalpy change when 1 mole of gaseous atom gain 1 mole of electron. Copy this. I'll tell you another form you can remember this.
So I wrote my answer. Is it correct?
Yeah, let's see. Now, correct.
Correct. Is it?
Take copy this after finish coming with thumbs up.
So done.
Okay. Then this one, write the equation as well. The easiest way for electron affinities, like ionization, write the equation, then convert the equation into what? So write gas is gain 1 mole of electron. So energy taken for can you see this 1 mole, 1 mole. You can use that. You can say enthalpy change when 1 mole of gaseous atom gain 1 mole of electrons forming 1 mole of gaseous negative ions. Negative -1 ions. Gaseous -1 ion. So if it is a second electron affinity, again you can write the second electron affinity equation. Do you remember that ACE level we did first ionization, second ionization? So
Yes,
similarly
sir.
it will go. Though the second electron affinity equation here. So this one if we say, so write minus gas here. Minus gas, it will form. No, again it will be in here. 1 mole of electron form. It's imaginary one, but this is possible. So did you get? Now this is fluorine, second electron affinity. So this is enthalpy change when 1 mole of gaseous -1 ion gain 1 mole of electron forming 1 mole of gaseous 2 minus ions. Write the equations and write the definitions. For the second one, we'll put something like oxygen. No, it's better. Fluorine is possible, but we put oxygen.
So,
Yeah.
so for the second electron affinity, sir, then of course when we are speaking, we have to speak first about the -1 ions converting to
Yeah, that's
minus
what.
2
Then tell
ions,
it.
not
Yeah,
atoms.
correct. First one, first electron affinity, we say enthalpy change 1 mole of gaseous atom gain 1 mole of electrons forming a 1 mole of gaseous -1 charge ions. But this one start with 1 mole of gaseous -1 ions gain 1 mole of electrons forming 1 mole of gaseous 2 minus ions. Okay, copy that and write the invert. These things we have to buy hard. Copy that and write inverts.
So normally we can say for the first one,
Yeah. Yeah. Copy that and write again underneath. Write this. This should go to your brain. So this is 1 mole of gaseous atoms gain 1 mole of electrons forming 1 mole of gaseous -1 ion. This is gaseous -1. This is second electron effect. Gaseous 1 mole of gaseous 1 mole should be there. 1 mole of 1 mole of gaseous -1 ion gaining 1 mole of electron forming a 1 mole of gaseous 2 minus ions. It's very easy when you
so,
read with the rhythm. Huh? Yes.
so this is normally energy released and this is energy absorbed. Is it?
No, don't use that word. Use the enthalpy change. Then there is no issue. No? Get used this word. Don't use the energy release, energy absorb. Can you say enthalpy change? So if then we don't have to think about something else also, getting it. So the second electron affinity is positive, first electron affinity is negative. That's a complex situation. Then if I use energy release, energy gain, this will mess up the system. Get it? Now, easy way to get the mass. So always use, when you use enthalpy change, we don't have to mention whether it's positive or negative. Getting it? The shortcut. Always tell enthalpy change. Otherwise, there is issue that the second electron affinity is positive. So gain release, don't talk about it. This is easy. So you remember, no? Second electron affinity, first electron affinity is going down, but second electron affinity is going up. It's positive. So let's use the term enthalpy change. You always must find the easier ways to score the marks. Lesser we memorize, it's better. But this you should know. Extra empty. Now you define with enthalpy change, but this is going down. This is exothermic, but second electron affinity is endothermic. The reason for this is when we take one electron, next electron will be repelled. It's really hard to take the next electron. That's why second electron affinity is endothermic. Somewhere write down again this. You must remember this. First electron affinity is exothermic, but the second electron affinity or the third one after second electron affinity is endothermic. Write that.
So is the answer I wrote correct, sir?
Okay. N-type chain, when 1 mole of negative ions gain 1 mole of electron in gaseous state to form 1 mole of you do not say 2 minus ions of that
So for the first equation, sir, the one.
ion. Okay, correct. Minus charge. Correct. Yes. I was in the first electron. I think. Correct. Then somewhere write down this first electron affinity is negative, but second electron affinity is positive. There's a reason for that. We'll write the reason of the basic things we have memorized. Reason for that is now, when there is an extra electron in the outer orbital, oxygen has 6 electrons. When he get 1 electron from outside, now next incoming electron, these 2 electrons will repel each other. This fellow and this fellow will repel each other. So it's really hard for him to come and get attached. So there's now this is a charge atom. So now this ion, early it was atom. It is not having a charge, therefore the electron can come in. But the second time, write like this, okay? Second electron affinity is positive. But first electron affinity is negative. Negative means it will normally happen in all exothermic reaction. Usually it will happen very easy. Endothermic sometimes happen, sometimes not possible. After finish copying your thumbs up. Done?
Done, sir.
Okay. Research done? Done? Okay, then we'll go to next one. This one I did not do it yet, but we'll write it down. Okay, there's something called entropy. Later we'll be learning it. Write down. Explain what is meant by entropy. The answer will be number of possible arrangements of particle and energy in a system. Entropy. Did not do the chapter. Yes. Entropy is number of possible arrangements of particles and energy in a system. Entropy is number of possible arrangements of particles and energy in a system.
So it's standard enthalpy change of entropy.
Yeah, it's correct.
So it's entropy or standard enthalpy change of entropy.
There's no standard entropy because this will happen in different temperatures. That entropy. Yeah,
So it's denoted by S.
yes, yes. Entropy is yes. Sometimes delta S. Change in entropy is delta S. Okay, the entropy is S. Change in entropy is delta S. So we'll go to next one. That one we have to do the chapter. This you know. What's from AS level onward, do you know what is a homogeneous catalyst and heterogeneous catalyst?
So homogeneous catalyst is a catalyst which is present in the same phase of the reactance of the reaction. It's the
Correct.
catalyst of the reaction.
Yeah. Heterogeneous one, different
The
state
opposite.
as, yes, different state as the reactions here. Right
So
one.
the reactance present in the reaction which the catalyst is being used on is different.
Yeah, correct. Heterogeneous catalyst and this back to back it says. There's some, this part is down. So there's something else also copied there. This part. Homogeneous catalyst is the same state as the reactants. Heterogeneous catalyst is in a different state as the reactants. Don't say phase, use the state word. State, use phase. State is better. Homogeneous catalyst is same state as the reactants. Heterogeneous catalyst is different state to reactants.
Concept.
Next one.
The state is better than phase because it's safe.
Yes, state is better. Don't say phase. Go to next one. Then they are saying iodide ion react with ferrodisulfate ions like this. This reaction is slow, but it is catalyzed by Fe2 plus ions. Write two equations to explain how this it's catalyzed. So that's when I have to break it into two steps. I have to break it into two steps. Final answer should be this. And you have to get it. Okay. Okay, right? Okay. 2y. Not exactly, Nikhil. That those are half equation. Without half equation, we can break it in two steps. Putting elements and last week what did it? We don't put half equation to break. Yeah, 2y. Anyway, 2y, I2. Okay, you're putting Fe2 plus. That's correct. You can put Fe2 plus there. Other side, you have to balance that now. The first equation, can you see you don't have Fe in there, so you can put there. It's if it is Fe2 plus, no, not Fe2 plus. Okay, now if you put, suppose we put Fe2 plus there, then the charge is not balanced. No, we can put Fe3 plus there. Left hand side charge is how much? You have plus 4 minus 2 plus 2. There can be any form. We say whether first equation whether you balance the charge. No, you can't do it. Your element is not balanced. Can you see the first equation? Iron element is not balanced. Left hand side you have 2 iron atoms. Right hand side you have 3 iron. Okay. Now if I put it like this, charge won't balance. So what the only way I can balance the first one is, first one we have to put a Fe2 plus. Second one we have to put Fe3 plus. Other side, Fe3 plus. Now the iron is balanced. Charge is it balanced? Now your charge is not balanced. Left hand side you have 0 charge. You're putting 3 Fe and 2 Fe. Again, the issue, iron is not balanced. You have to balance the iron as well. What you can do is, rather than putting I minus one of them, you can put one I minus there. We'll keep Fe2 plus and Fe3 plus. Then other side, you have to put half I2. Half I2. Then next equation, you must make sure you are getting I2 and I
Sir,
minus again.
so here it's going to be +1, here +3.
Let's say plus 3. Oh, there's issue. There's issue. Got this. Plus 1 and then plus 3. Can't wait. Then you have to put some I minus in the other side then, no?
Yes, sir.
Can't buy. They put a 2 I minus. What will happen? Yes, sir, somehow you have to balance the charge and figure out a way. There are many ways you can do it. What are you going to do? You put 2I minus, put it there. Put the 2I minus what you put earlier. That's correct. So you put 2I minus. Okay, now there's a charge issue. So to get rid of the charge issue, you have to put Fe2 plus and Fe3 plus. Correct. Fe2 plus, yes. Next one you have to put Fe2 3 plus. Fe3 plus. Now we'll try to balance left hand side and right hand side. Left hand side and right hand side, if you put 2 Fe, 2 Fe, it will balance. No? Put 2. Okay, 2 and 2, it will balance. Now, okay, no? +4 minus 2 is +2. This
So the charge still is unbalanced. +2 here and +6.
Then we'll put left hand side 3 plus, right hand side 2 plus. No, then correct. Left
Sir,
hand
normally
left.
here, sir,
Ah,
the
yeah,
+3
that's
would.
what we have check this. No, there's something issue. No? We didn't check something. Now, this is the oxidation. So, this also can't be oxidation. This should be reduction. Go from 3 plus to 2 plus. That's why it's not balancing. It can't happen. 3 plus 2 plus should be other way around. 3 plus 2 plus, correct. Then if I put both 2, 2, it will balance. Now, okay. Okay, now write the other equation.
Sir,
Yes.
so here the 2 Fe3 plus, this overall will be producing +6, is it, sir? Like 2 into
This side,
+2.
no, this side +6 minus 2, it will be +4, correct? Other side also +4.
So this loan, like we take just Fe3 plus N2, this has overall charge of +6, is it, sir? Like +3 from each Fe ion.
Correct, correct.
That we normally take it like that, is it, sir? We don't take like
That one, you can
+3,
balance it like
+3.
that. Balance with the electrons as well, yes. Okay, this is fine. Okay, try the other one. I'll write another one with explaining. Try the other one. Your first one is now H2O minus. Okay, you're going to do that. 2SO4 minus, correct, but I had to get that overall equation. Am I getting that overall equation? Hmm. When you add it, I have to cancel out that. No, correct, correct. Now you put the, no, to get the overall equation, I had to put them again back here. These two fellows, I had to put them back here. Here. Way of cancelling off. They're not that way, other way. This way, if I add it, will it cancel out? Yeah, correct. That's this side 2 5. That's correct. This side 2 plus, that's correct. This side 2 plus, this side should be 3 plus. Now we have to balance the charge. We have to balance the charge. Left hand side Again, if I put 2, 2, it will balance. No? Both sides put 2, 2. 2 Fe2 plus 2 Fe2. Okay. Now the overall one, draw the overall one whether we had done it properly.
Yes,
If
sir.
done properly, overall
So,
one.
so in the product side, sir, it's going to be -4 plus 6 to give
Yeah, plus
plus
2.
2.
Plus 2. Right hand side also -4 plus 6. Yes, correct. No,
So
plus
this is going to be
-2 plus 2
2.
plus 6 -4 plus 2. Correct. Both side plus 2.
So 2 into -2 plus and 2 into minus, so plus 3.
Correct. Both sides.
Correctly?
Copy that.
And so in the product side, sir, it's going to be +2 into 2 and
Correct. Correct.
-2
Yeah,
into
correct.
1.
Okay, copy that. Then I'll do another one. Correct. So there are many.
Sir,
Somehow we have to figure out a way of showing iron as a catalyst because he's appearing. Can you see? He's appearing in here and here. If something appear here, iron 3 plus is the catalyst. Actually, iron 2 plus is what? Iron 2 plus is called
cyan 2 plus
intermediate. Last week we did that.
intermediate. Yes.
Iron 3 plus, but the iron is the catalyst. Somehow iron is the catalyst. According to your equation, iron 3 plus is the catalyst. Others when you're done, give a thumbs up. I'll show you how to get another equation like this. There are many, not this. There are many ways you can write these answers.
Good answer.
Lisa, when you're done, give a thumbs up. Okay, I'll explain. Same. But the key contract is final. That overall equation we should get somehow. We should get that somehow. That first I'll copy this overall equation. I have is 2I minus plus S2 2 minus I2 plus 2 SO4 2 minus. I'll tell you what to do. In a case like this, I'll give you some standard ways of doing this. This one, break it in two pieces. Take these two as one equal. These two as one equal. These two as first write like that. 1, 2, it does not matter. The order does not matter. So I'll write is 2 OA 2 minus, and these two as 1 plus 2 SO4 2 minus. That's my one equation. Then the other equation is 2I minus is going to I. Now I know if Fe2 and Fe3, I have to plug this in. That's all. Actually, you had to use your ACE level knowledge to do this by 2 steps. Really, you should be fast. Now, for example, this one I have to couple with first equation. If Fe2 plus is going to Fe3 plus. This one I have to couple with if Fe2 plus is going now. Here, see, we have an equation. Forward or backward, you have to couple depending on the sum. If Fe2 plus Fe3 plus, you need one electron there, one electron to do that. On this one, I can couple it and put it there. So we'll do it now. If you do it in the ACE level way, it will take some time. I'll show the ACE level way and I'll show shortcut here. We can't do the ACE level way because it's consumed time. But I'll show the ACE level way. Next to 2, 2 minus. If I want to couple it, now first I have to check with the oxidation reduction mean. So here we see what's the oxidation number of this? 2x minus 8 is equal to -2. That's been
So plus 7. +7, say, for this alpha atom.
-16. So this -16. Then -16 goes to +7. This alpha is +7 here. This one will be x -8 is
+6.
+6. So this went under reduction. No? So this goes under reduction. This should go under oxidation. That's correct. So this is going into oxidation. 2SO4. Now, if it is difficult for few sounds when you are doing, do the S level. But I'm going to get this. I want to couple this with this and get the overall equation and write it there.
Sir,
So the,
excuse me, sir.
so now
So the SO4 2 minus 1, sir, the product side, it has overall charge of -4, is it, sir? Because -2 into 2.
yeah, correct. Now I'm doing the S level, so we'll see how to balance this. Huh? Now, to balance this side I have 2 minus, this side I have 1. All the other elements are balanced. Elements are balanced. So this is 2 minus, this is 4 minus. So if I add 2 electrons here, it will balance, no? If I add 2 electrons there, now the equation is balanced. So now what do we do in S level? We multiply this by 2.
Times the upper one by 2.
Multiply by this by 2. This is 1. This by 1, we add it. So when I get the overall equation, it will be 2 Fe2 plus S2O8 2 minus will form what? 2 Fe3 plus 2 SO4 2 minus. We got that equation, we had put it there. In other words, we got the Fe part only. See? Fe was balanced and we got it. So I know now this part should be written as I must have a 2 Fe2 in this side, 2 plus in this side, and I must have 2 Fe3 plus in this side. Then later we'll fill this. Copy this part for the moment. I'm teaching you the S level there.
Sir,
Yes.
excuse me, sir.
Yes, tell me. Yes.
Sir, so normally afterwards we do it for the I1 as well, and then we add both of them.
Yeah, I1 also I do the S level. First I'll show you the S level, right? Then we'll try to do it with a shortcut because we can't waste time like that. No, this is the normal way of doing it. S level now this is the overall equation. I'm getting it by 2 half equation. This way also fine if you have time. I'll copy this, but I'll show you a shortcut as well.
Done, sir.
Okay. So you can listen if you are done, give a thumbs up. Then this is the shortcut. Huh? If you want to do this quickly, this is what we do. First check this. Now I'm telling you how to skip this. They are not asking this, but they are not asking half equation. So why do you waste time on half equation? Now yes, there was something. Now here was they asked half equations in electrode potentials. Now this sum they don't. Now here elements are balanced. Elements are balanced. Elements are balanced. But this one is going from +7 to +1. This one is going from this equation. Elements are balanced on this fellow. In other words, this fellow is balanced. Okay. So he is going from +7 to +1, +7 to +6. Okay.
Just reducing it there, so the
Yeah, so it's, therefore, he will be taking, if I observe it, he will be taking 1. 1 is 2, will take 1. But there are 2 is 2 transferring. 1 is 2, will take 1. Oh, you take it like this now. If you refer to the number here, this is 1. So this one equation, it will be having a transfer of 2 electrons. If you check the charge also, you can get it from check the charge also can, no? If I want to balance it, now the same thing, forget about this. That is to check the oxidation and reduction. First you have to check this, okay? This is what you have to check. I'll go by step. This one I know, this was +7, this went to +6. First thing is, I have to figure out which side I have to put Fe2 plus and Fe3 plus. That means Now this will go under reduction. So I need oxidation here. First thing is I'll be writing Fp2 plus here. Then I'll be writing Fp3 plus here. That is my first thing. That, how did I check that? Checking these two numbers, plus 7 and plus 6, checking those two numbers, only I check that. Got it? Checking those two numbers.
So,
Yes.
so that's reduction, is it?
This is reduction, no? No, this is a
Yes, sir.
reduction. Therefore, that's oxidation. We wrote that. Okay, now I am erasing this. Plus 7 and plus 6, I am erasing. Now, AS level equation, keep in your mind. Now, if I have here to here, I have to add 2 electrons now. This 2 electrons I am talking about. So those 2 electrons, you can use a pencil and put the 2 electrons here. Here to here, that these 2 electrons, we are not putting it here, we are putting on the arrow. Getting it? 2 electrons, arrow. But okay. Now, other fellows also, this 1 electron, no? Other fellows are involved with 1 electron, it should be on the arrow. Getting it? Then to balance the electrons, I have to multiply this fellows by 2, this fellow by 1. Getting it? 2 here, 2 here. Did you understand? This is, they are now in a short form. So I did not put this electron in a side. If I put the arrow, I'll put it this way. He took the electron this way. I showed it with arrow. Did you understand? Give a thumbs up. This same thing is there in the short form. I multiply this by 2 because I want to balance that equation. I multiply this by 1. Did you understand that? It's the same thing. We did not write this complex way. Your thumbs up, did you understand that?
Yeah,
This
I got half of it, sir, but the last part,
which it's say now for example like this. Now I have to write this equation. If I have to write this equation, I have to put plus 2e here. Instead of putting plus 2e here, I put the plus 2e there. Did you see that? And instead of putting e here, because this one will lose electron. This is e, this side minus e. No? So that I showed it there. Understood? No.
so the times in by 2 is my.
Multiply by 2 is that is now this one has a transfer of 1 electron, but this one has a transfer of 2 electrons. No? So I have to balance
Ah,
the
okay, sir.
electron.
We like cross multiply
It's the
that one
same thing.
by
It's the
2.
same thing. Same
Understood, sir,
thing.
understood.
This one I multiply by 2. This one I had multiply by 1. So these two places I will be multiplying it by 1. See? These two places I multiply by 1. 2. Chanu, can listen? Did you understand? Did not tell. This one, now the short form there. Okay. No? So now normally when they are not asking half equation, but they ask in electron potential, there's a chapter called electron potential. There they'll ask. But if they're not asking, we'll do it this. Now same thing we'll do it to the next one. Okay, after finish, copy this part. We'll do part by part. Separate the diagram should be. Don't write it everything at once. Then you don't remember it. Near the exam, you'll be referring the book. No, then you can't understand what you have done. So write this part separately now. Again, we'll rewrite. The full thing, write it separately. We are far away from real exam, but now we have time. We can take time and discuss these things slowly.
So should I write the whole thing?
Yeah, after finish copying, the full thing copy it. Huh? After finish copying, give a thumbs up. Then again, we had to do a double equation for this. Then we had to prefer the shortcut of that. I'll finish coming the answer. When you're done, give thumbs up. I don't know, the channel can listen. Nikhil, when you're done, tell.
So I'm in the last part, sir.
Okay, fine. Waiting for Nikhil.
Good answer.
Okay, now, next one. Again, we have to do the same. That part is done. It's 2, 3, 2 minus 2 minus 2 plus. This one also, again, I have to check like this. If I do in the ace level way, I do it like this 2I minus I2. First, I have to check. This is going from -1 to 0. No? This is going from -1 to 0 means going under oxidation. Therefore, ion should go under reduction. And another way I can see, either way I want to cancel off ion. Either way, it's a catalyst. So it should be cancelled off. It can't be there in the overall equation. So therefore, Fe3 plus should be in this side and Fe2 plus should be in that side. That right? Okay, then to balance this equation, this one I have to add the electron to this side. This one, if I do, I have to add 2 electrons this side. No? 2 electrons this side. Again, same thing. I had to multiply this by 1, this by 2, and then I have to add it. So the ace level way of doing this is 2I minus plus Fe2 to Fe3 plus 2 Fe2 plus I2. That is the ace level. Now A level, so we'll do this way. Now I'll check this fellow first. First I am checking out. This is going from minus to 0, therefore it's going under oxidation. Therefore, I know other fellow should go under reduction. Other fellow go under reduction means it should be Fe3 plus should go to Fe2 plus. Okay. Then I'll check. I will be checking the electron transfer. So from here to here to balance these two. To balance these two, I have to lose 2 electrons. So this way I have to lose 2 electrons. So this way I have to add 2 electrons, lose 2 electrons. Here to here, gain 1 electron, gain 1 electron. That's enough. Now I realize this should be multiplied by 2. This should be multiplied by 1. So therefore, I'll put 1 here. I multiply 1. That is, I'm keeping it the same. I'm not changing anything. But this should be multiplied by 2. No, there's a 2 appearing here, 2 appearing here. Copy it again.
Sir,
Understood?
could you explain the last part, sir?
How this one, no? How I got this? I will now explain.
Yes, sir.
Let's see how I got it.
So that's because of that going under oxidation. So the
Yeah,
other one must
oxidation
act
and
as
reduction, we put the sides correctly. See, now I put the sides correctly, but the equation is not balanced. I know this is going under oxidation, therefore this should go under reduction. This is 3 plus,
understood, sir.
that is fine. Now I will think about the electron, the same as this. We are arrow wise, we are thinking. So now I realize here to here, I'll write these 2 electrons in this side, then it will be clear. So I'll write 2 electrons. So I know here to here, you lost 2 electrons. But here to here, you will be gaining 1 electron on. Lost or gain, it does not matter. I'll just put without the sign. This is a transfer of 1 electron. This is a transfer of 2 electrons. Now I had to balance the electron. So to balance the electron, I realized I had to multiply this by 2. So I'll put 2 here, 2 here. Do another sum like this, then we'll get hold of this copy.
Got it, sir.
So after finish copying the thumbs up.
Sir,
Yes, sir. Yeah.
sir, here it must be 2i minus plus minus 2i.
No, it doesn't matter. You can write plus minus 2 electrons. But you can write minus 2 electrons. Don't put plus minus 2 electron. There is a small issue. Then examiner think you will be tricking it, getting it. Now if you put here also if you put minus plus 2 electron, yes, it's losing electron. How can you add then lose it? It's mathematically correct, but this does not look like chemistry wise that plus is not that good. Huh? Examiner think you are trying to trick him. It's losing. Then normally this side we write minus 2 electron, that side what? Plus 2 electrons.
Sir, we normally deal with this charge like in this case, like if we get 3al
No,
3
no,
plus, we just like times this by 3 to get it as plus 9 as the total charge.
we'll go for a little lower. See this? Sodium. There's only one. Normally we write that is sodium plus either sodium minus 1 electron. Sodium will become what? Plus. Oh, you can write sodium will become sodium plus the electron there. What you're telling is correct. I can write a plus minus there, but it's not a good idea. The chemical wise, I'm going to give that idea. Either way, it's losing electron. Mathematically, it's correct plus minus. So this is the
Sir,
way I used to either this way or either that way.
so this is like minus e minus.
There's a don't okay, minus e minus 1. E is minus, that is fine. You put the charge for E is minus, fine. But not that I'm telling this minus and this plus, keep it like that. They don't put plus minus C.
Got it, sir. Sir, I have a small issue, sir. Like in individual species, sir, like if we take Fp 3 plus, like if it has a coefficient of 4, then it would be 4 into plus 3 with the overall charge of plus 12, is it?
Correct, plus 2. That's correct. It has a overall charge of plus 2. That's correct.
So that's not for the whole thing. So it's like individually plus three into four sets and then form plus 12.
Yeah, so so this part will have a charge of overall charge of plus 12. That's correct. Yeah, plus 3, 4 of them are there. Okay, now after finish configure also. So these are the few possible ways of writing this equation. Actually, only two possible ways. What we wrote
Fancy.
earlier, okay? What we wrote earlier is Nikhil did it like this. No? If you noticed the earlier one, we broke it earlier. There are only two possible ways you can break it. Huh? There are other ways. Don't think that much. Huh? So either you break it, first write these two, second write these two. Or you can write first these two. First I can write 2i minus n I2. The second I can write S2O8 2 minus and 2SO4 2 minus. The iron is the catalyst now. So balancing me, I had to put it. So we'll do it quickly now. Earlier one, we'll do it quickly. So now I realize this will go onward. Iron is balanced. Now these things are balanced. Elements are balanced. Charges are not balanced. See, this one charge is not balanced. Therefore, I have to subtract 2 electrons there. No? For this fellow, I have to subtract 2 electrons. So losing electrons mean it's going under, we can check it like that also, no? Subtract 2 electrons mean losing electrons, that's going under oxidation. So if this is going under oxidation, iron should go under reduction. Iron should go under reduction. Fe3 plus Fe2 plus. Iron will go under reduction. Then I realize this is the transfer of 1 electron. That is a gaining of 1 electron. Therefore, I realize, now the important thing, therefore I realize this should be multiplied by 2. That's in here I have put a 2 and here I have put a 2. But this should be multiplied by 1. That's in this should be multiplied by 1. That should be multiplied by 1. I'll show it. This should be multiplied by 1. That's in this should be multiplied by 1. This should be multiplied by 1. Now we are doing it quickly. Okay, for practice. Understood, no? Okay, copy that, then I'll complete for this part. These are the two possible ways of doing this sum. The breaking way only difference. Either you have to take the I2 first. Now this time I'm taking I2 first. Sulfate circuit. That same equation, it's going upside down. There are other possibilities later we'll discuss. Now we are in the beginning of this stuff, no? But still it's little confusing. No?
So this is the same sum done in another,
Other
the
way
way
around,
we
same
which we
thing.
did.
Yeah, we switch the order. That's all. Of this and
So I did. So should we write that as well? The one which,
yeah, right. This yes, it will go to your brain. Now we are not writing. See, we are not writing the S level work now. We are trying to do it without the half. Not the S level, without the half equation, because we have half equation in electrode potentials. We have to write it again. Another chapter is coming now. For electrode potentials.
so the below arrow is 2 into what?
Huh? You said something?
Below, so the below arrow is 2 into
2 into 1 electron. No? 2 into 1 electron. Because this is a transfer of 1 electron.
okay. So that's still for the first step is the second step is into.
Okay. Done, no? Then
Done.
I'll erase the arrows, otherwise it's confusing here. Then what I have here is You check it. Now there, this is a 2 minus charge, but this is a 4 minus charge, so there the charge is not balanced. 2 minus, this is 4 minus. That's mean we have to lose, no? We lose 2 electrons. No, gain 2 electrons. We have to gain 2 electrons. Because 2 minus to go to 4 minus, I have to gain 2 electrons. So gaining electrons mean this will be going under reduction. So if this is going under reduction, iron should go under oxidation. So I realized my iron should go under oxidation. So I'll write the iron in oxidation format. As in
So then Fe
2 plus
2
here,
plus
Fe 3 plus here. Then I know iron will gain only 1 electron. This one is iron is losing one electron. I will lose 1 electron. Now I have to balance the electron. Now this losing gaining it does not matter. I just put it there that to check the order. If this is going under oxidation, other one will go under reduction. Now the multiplication balancing the electron. This is 2 electron, this is 1 electron. So this fellow should be multiplied by 2. I realize this fellow should be multiplied by 2. So 2 here, 2 here. Okay.
So oxidation is only identified when the oxidation state ideally starts to increase. Is it so?
Yeah, the oil ring. No? Remember the oil ring.
So when the oxidation number drops, then of course it's reduction.
Oxidation of?
So oxidation number, when it decreases, then of course it's reduction. Is it so?
Yes, oxidation number increases. Yeah, that's okay. Now rather than that's earlier we do this some by checking the oxidation number, but rather than we can check it from here. No? See, this is a 2 minus charge. 2 minus charge to go to 4 minus charge, it must gain 2 electrons. No? From there it's easier, no? Rather than checking this one oxidation number and that one oxidation number. Either way, we have to balance this electrons. No? So checking with this is easier. Got it, no? 2 minus to go to 4 minus, it must gain 2 more electrons.
So should we copy the third equation
Copy.
only?
Yeah, copy this, yes. Then we know the overall equation also we copy it now. The overall equation, of course, we know it will be that 2I minus S2O8 minus A2 plus 2SO4 2 minus. Copy.
So the blue color arrow minus, sorry, 2E minus into 1, isn't it?
So this is not minus, no? Plus 2 electrons, no? From
Ah,
here to here, if I were to go, because I am going from 2 minus to 4 minus. If I want to go from 2 minus to 4 minus, I must get 2 electrons. So therefore,
other one is
other one is lose
times
electron, no? From
the
2 plus, if
minus
I want to go
E
to 3 plus.
into 2.
Okay. From 2 plus, if I want to go to 3 plus, I have to get a minus. This minus and plus, it does not matter. We are just checking the oxidation and reduction from minus and plus.
So I had plus 2E minus is fine.
Yeah, fine. Okay. Copy 10 years. And we'll move to the next one. That you understood this. So here, I really, in this one, Fe3 plus is the catalyst, Fe2 plus is in, but in general, iron is the catalyst. But something like this species, we call it intermediate.
So now both sides are minus 4 because minus 2 plus minus 2 to give minus 4 in
Correct.
the reactant side. Minus 2 into 2 is equal to again minus 4, then in the reactant side. Sorry, product side. Is it?
Correct. Yeah.
Done, sir.
Okay, done. Shall we tell Lisa when you're done? Go thumbs up. Shall we done? Go to the next one. Then they're saying something interesting. Suggests why the alternative route in the presence of Fe2 plus ion have a lower activation energy than the route with absence of a catalyst. This is something different, some different answers. Now here the answer will be like this. Now can you see the reactants are both negative? So therefore they can't come together. Reactants, they repel each other. Reactants are both negative, they repel each other. Therefore they can't come together. Okay. But
Understood.
when you add the Fe2 plus can get attached to one reactor. Then he can what? Uh, he can help the continuation of the reaction. Getting it? The idea is initially the two reactants are negative charge. Okay? Two reactants are negatively charged, therefore they will repel each other. But Fe2 plus is positively charged, therefore it can what? Attract both of them and they can give it. This is what will happen. Huh? Now there's a rule like this. These are called surface catalysts. The surface catalyst will act like this. We'll tell the full story. This is 1 mark. We don't need to write the full story for 1 mark. This is how a surface catalyst will act. This is I. I minus, and other one was is 2O4 2. Like that. So that two reactions. No? Is 2O8. So can you say they will repel each other. The idea is they are repelling each other. They repel each other. And put them together. But this fellow can attract them. Once they attract them, this is called absorb.
Sir,
Here,
so this is surface catalyst.
here.
So it's absorbing or absorbing it?
No, not absorbing mean going in. No, this is absorbing like powder. Now, if I put some oil, if I put oil onto the skin, now we say Ayurvedic medicine, they put oil into the skin, what will happen? When you put, it will absorb. If I put water into the skin, it can go to the skin. That process is called absorb. This is adsorb, no? Adsorption. Absorbing or adsorption. Huh? And
So it's the opposite of absorption.
so, so huh? Opposite of what?
So it's opposite of absorption.
No, this is not, the opposite has a name. Okay? Now this is absorption. Opposite also has. Okay, we say adsorption. Now when they adsorb, what will happen? They can react. Good. We'll write the diagram. But this whole thing we must know. This is how catalysts work. Now when they adsorb, now he will pull them together. They can react. H2O8, they can react. Now they will form the product on the surface of the catalyst. They will form the product. So in this case, what are the products?
Yeah, I2 is SO4
I2 and 2SO4 So they form I2 and 2SO4 minus. So they now they can leave the surface. They can leave the surface. Now this one is called desorption. Okay, this is called desorption. You remember these two words. Huh? Not the absorption is not here. Absorption means like this. If I put paper inside the water, what will happen? Water will get absorbed. But if I put powder onto a paper, it's adsorption. Did you see the difference between absorption and absorption? Absorption, no, there is no absorption here. You have adsorption and desorption. We call it adsorption of reactants. This is called adsorption of reactants. Desorption of products. Desorption of
So
products.
that means, so both of these are surface catalysts.
No, it's the same reaction. No, it's iron is acting like a surface catalyst. Same reaction we are talking about. They can't react together. Why they can't react together? In this case,
Negative,
they are
negative.
negatively charged. But for example, something like Haber process, they will find it difficult to react together. Why? They are gases. No, gases molecules are randomly moving further apart. Getting it? They have low chance of meeting with each other. Nitrogen and hydrogen gas in the Haber process. So again, it's the same story. So when they get absorbed, they are in the same place now. Therefore, they can what? React. So difference of the reason is different. Now here the reason is they are negatively charged. Therefore, what? They are both in a solution. Therefore, little concentration is there, not like in a gas. But they are negatively charged. Therefore, what? They will repel each other in this case. But if it's a Haber process, I can't say they are repelling each other because
Sir,
nitrogen and hydrogen both are what? Neutral. But I can say in Haber process, we are using the same ion as a catalyst. They are gaseous molecules. Therefore, they are further apart. They are moving in random motion. Getting it? They have low chance of meeting.
sir,
Yes.
so here there's no repelling because this is a molecule and this is a negative species, so it would ideally be lost like desorption.
No, we'll talk about that in the transition metal. No, that's another thing. The reason is these fellows, that's why transition metal, good question. Okay, transition metal act like a catalyst. Transition metals, now, if they want to attract him, he should what? Get electrons from him. Getting it? So transition metals can do both ways because it has variable oxidation state. No? Whenever they need, we saw it in the equation, they can take electrons. So when someone want to make a bond, they'll take electron. So someone want to break free, they can do anyway. Can you say if they want, they take electron. If they want, they'll give you electron. So you can come and go any way you like. Getting it? With the transition metal. The reason of the variable oxidation state. Now sodium can't do that. Now sodium can only what? Give electrons. Getting it? Sodium can give electrons only. He can't do anything else. Chlorine can take electrons only. But can you see iron? If you want, he can take electrons as well as what? It can give electrons. Therefore, that's why they can work as a catalyst. Whenever they want, they can form bonds. Whenever they want, they can break bonds. Getting it? So that's the
So got
property.
it.
Yeah, that's the property of a transition metal. We have a separate chapter for that. We will be doing it that way. That's the property. Why transition metals can do that? The reason for that is they can go under oxidation as well as reduction. Sodium can go under only one. Losing electrons. No. Losing electrons is sodium can oxidize only. Like this also. This is how it works. You got the meaning of the two terms. No? So there is no absorption here. Absorption is something like oil can absorb into your skin. Water can absorb to a paper, but powder is a good example. Powder is adsorption. Powder can adsorb to the skin or the paper.
So should we write those two in the book?
Yeah, adsorption of reactants and desorption of products also right. With that right. Like this.
So what's the heading?
No, not the heading. Under the same sum you can write. We are talking about catalyst. Catalyst. Yes, say catalyst. Surface catalyst you can say. But we are right for this one you don't have to write everything. We can just say what the reactants are negatively charged, therefore they repel each other. We don't have to tell the full story.
Sure, okay.
Yeah, copy this.
So that's H2O8 2 minus, is it?
H2O8 2 minus. Yes, that's the reactance.
So you have written that arrow outwards on F. What is that F, sir?
No, I am giving this idea. They are repelling each other. The force of repulsion force, electrostatic repulsion, Coulomb repulsion. I'm giving the idea they are repelling each other, so they can't meet.
So that's the Coulomb force, is it?
Coulomb force. These are Coulomb repulsive forces. Force is a force. Coulomb force. Electrostatic.
So Fe is just going to be just Fe, not a charged Fe, is it?
Yeah, which one?
The Fe below, sir, that's not going to be
No,
charged, is it?
he can get charged, but we are referring to the normal ion catalyst. He can become anything, no? When he want, he can become Fe2 plus. When he want, he can become Fe3 plus. If we just mark
So
it up.
that's why you cannot write a proper charge.
Yeah, for the moment we don't. When we wrote then what's going on in there while that this is happening. When he want to absorb, he went from Fe this one. No, to, when he want to react with him, he'll go in from Fe2 plus to Fe. For him, it's a different story like that.
So, sir, in the second diagram, you have written the charge outside of that circle. Is it fine if I write it inside?
Yeah, desorption of the products. So once the products are made, they will leave the surface. They will leave the catalyst. That's why you call it desorption of the product.
So this part, sir, like why is the charge outside here? It's inside.
No, this I circled it. This is not, this is mine. I was for the diagram, I said you can do it anyway. These are my circles. I'm just showing it. You can put it
Got it.
outside to inside. Just a minute. It's my circle. It's iron, but the one, this is not the way normally we write that. That's fine. Iron we write like that. It's this okay. I circle. Here diagram. Outside or inside, it does not. I circle it to show that is a separate time.
So that's desorption of products. Is it, sir? Not product.
Desorption of the product. You have to buy half this. Okay, absorption of the reactants, and this will always happen. How the surface catalyst react, you write this answer. Absorption of the reactants and desorption of the products.
Should we write like an arrow from to show where the absorption and
Yeah,
desorption
correct,
occur?
correct. Absorption mean going in, desorption mean going out.
So the topic I wrote was surface catalyst.
Surface catalyst, fine. Okay. Then after finish topic with thumbs up, but this some simple answer is enough, 1 mark. Third one. Except nickel when
Trans-
okay, then I'll go to this one. A very simple answer is enough. We can tell what in a case like this, you can tell both reactants are negatively charged. Therefore, they will repel each other. That other story, no need for 2 marks. So 1 mark. If it is 3, 4 marks only, we have to tell the full story. So here the answer is reactants are
So the third part one is it?
a third part. Both reactants are negatively charged, therefore they will repel each other. If you want addition, you can say when ion is around, it can what? Absorb the reactions. When ion is around, it can absorb the reactions.
So both reactants are negatively charged.
Therefore, they repel each other. Therefore, they repel each other. Both reactants are negatively charged. Therefore, they repel each other. Then you can say that's enough for this sum, but we'll say other part of that we'll say iron. This is iron 2 plus. So iron can absorb both.
So adsorb is AD.
AD absorb both.
So I wrote Fe2 plus can adsorb.
Absorb is correct.
Not just ion is it? I wrote Fe2 plus.
Fe2 plus fine. Absorb by. Okay, then they are having nitrogen monoxide react with oxygen. This reaction is second order with respect to nitrogen or first order with respect to oxygen. Write the equation, rate the equation they are asking to write. First order with respect to nitrogen monoxide, second order respect to oxygen.
So the rate equation for the whole thing.
Yeah, K, and we'll write with the square bracket with the powers. Write the equation. K is correct. K square bracket nitrogen monoxide power. Side power is oxygen. So 2. Now we have to put the correct powers. Second order respect to nitrogen monoxide, first order respect to, yeah, that's correct.
So I got this. So we get the order form like due to 2n, no? The 2 is the power.
Yeah, that will come as a power. That's correct. Rate equation, it will come as a power. Okay, now we have to put the values and find the calculate initial rate of reaction under this condition. Yes. K also we know, concentration also we know. Yes, fine. Put the values and multiply.
The initial.
Yeah,
So
there.
we should find the rate is this
Yeah.
one.
Into 10 to the power 6, that's correct.
So between the brackets, like power to like n to power to, then it's times is it, not addition.
No, if you type it as it is in the calculator, then it will come automatically. What you have on the screen, exactly type on the calculator, then no issue. Don't think about the power, just type it as it is in the calculator. 8.6 in 10 to the power 6 multiplication, put a bracket, 7.2 in 10 to the power minus 4, close the bracket, power 2, as it is in the calculator, type it in the screen. Then you get the answer. In the power minus. No, we typed it wrong. Again type, power is wrong.
So I write it again, I got the same answer.
No, others correct is power. Typing error. What you wrote on the screen is exactly correct. Typing error.
So I did was 8.6 into 10 to the power 6.
Into bracket 7.2
So
into
it's power minus 3, is it?
Last one minus clear. Final answer. Correct. Minus clear. That's the answer. What's
The power on the NO and O normally is taken by the coefficient in front of the reactance.
Don't think about the maths part here. Just type it in the calculator. Yes. Here, if you remove that bracket, 7.2 to the power 2 will come, 10 to the power minus 8 come. Don't think about that much. Chemistry, you don't have to think about power calculation. That type it as in the calculator. If you start thinking about those things, everything will get complex. So then what's unit? Rate unit. You have normally by heart the rate unit. No, K only we calculate unit and get it. Rate unit will never change. Yes, mole per decimeter cube per second. Rate unit will never change. Yeah? But the K unit from some to some it will change. Rate unit won't change. Mole per decimeter cube per second. Copy that?
Should we write this with the question number?
Yes, no, they here. This part, no, answer is there. No, they gave the unit, no, mole per decimeter cube. They gave the unit. Okay, I'll finish covering the thumbs up.
Answer.
Okay, no? Others, when you're done, give an answer. Channel, if you're done, give a thumbs up. Then is copy. Go to other part. That's it. So something that the drug cisplatin hydrolyzing wood. The rate equation is shown. The value of K, rate constant is given. Then reaction has a constant half-life. Why the reaction is having constant half-life? What's the reason?
So the order is ideally order is 1.
Yes, order is 1. Yes, we can say overall order of the reaction is 1. When the order is 1, we know the half-life is constant. Okay, right. Reaction is first order. Overall also first order. Okay. Total overall load is 1, hence the half-life would be constant. Then they are telling, they gave the K, they are asking the half-life. Now there are some physics equation very handy in here. All half-life equations are same, no? But the issue is physics papers, they'll be giving it at the end. Chemistry papers, you have to memorize. Okay, so they, when they write the equation, when we do the half-life in this is it's easier for this. Okay. So now in physics radioactivity activity. Activity is measured in becquerel, no, that's disintegration per second. So if it is 5 becquerels, disintegration per second. Okay. So A stands for activity. So we say A is equal to, we have equation A naught e to the power minus lambda, mean this is the rate constant T. Rate constant T. Then there's another equation T half life. T half life is equal to ln2 divided by that K. Now this is true. Okay, this equation is valid in radioactive physics. In physics, radioactivity. Radioactivity, the graph is same. Huh? Radioactivity also we have a graph like that. Capacitors also we have a graph like that. Physics, radioactive and capacitors.
So that's radioactivity and radioactivity or
Capacitors in
radioactive.
physics. Huh? So same equation can be used in chemistry. Rate. Rate of a reaction, half-life. You can use the same thing. So now, for example, this radioactivity, this activity versus time. Radioactivity. Capacitor, it will be current versus time. When we come to chapter, I'll say current versus time. So it will be, this is the initial current, that will be the final current. Now here, again, rate versus time. Oh, but these two equations, but there are other ways you can get the answer. O-level way also valid. Huh? Now for chemistry, we can get the answer with O-level way. I'll show it, but if you know this is easy. They'll give you the full marks with this question. Huh? Yes, tell.
So how to get using? Should we use both the equations which are
No, I'll
given?
tell you how to handle it. Yeah. Different sums, it differently. You copy that? That will take few minutes and we'll discuss this. How to handle this. All three subjects will separately teach. I teach.
Should we copy the whole thing?
Yeah, copy the whole thing. I'll start with physics here. It's easy. Physics radioactivity, then I'll explain it with chemistry. Capacitors we'll later do. We are familiar with physics radioactivity.
So that's A
A
zero.
naught stands for initial. Huh? Initial activity. A naught stands for initial activity. Not here in your throughout further studies. Whether you do medicine or whether you do engineering, it does not matter. Throughout your further studies, you will be having these exponential functions and their half-lives. You have to deal with them. So now you can see the same thing is appearing in two subjects. But in your further studies, you'll see it will be there in many subjects.
So it's radioactivity and capacitors. Is it?
Capacitors in physics. Chemistry, rate of reaction. K is the rate constant. K is the rate constant.
So for chemistry, it's just rate. Is it?
Rate constant. No, not rate of reaction, it's rate constant. K. Rate constant is K.
So like the equation can be used for chemistry in terms of rate only. The two
Okay.
equations.
Rate chapter is rate. Yes, correct. Rate of reaction.
We can
Rate.
just like
Yeah,
write rate. Is it?
yeah, rate of reaction. The chapter is here. The chapter is capacitors and radioactivity. Here, rate of reaction. Rate of reaction chapter only we use it.
So the graph is same. Is it?
Graph, all graphs are same. It's exponential decay, right? Half-life graph, but you did in all graph.
Understood.
Okay, after finish covering the thumbs up, I'll start with the chemistry radioactivity. It's easier. Not chemistry, physics radioactivity.
So what is that other one, sir?
Which
The
one?
first graph, INT.
Current. If it's capacitor, we write current with time. Current will drop with time in capacitors. Radioactivity, activity will drop time. Radioactivity, the activity of the sample will drop with time. Rate, the speed of reaction will drop with time. Okay, when you're done,
Okay,
give
sir.
thumbs up.
That's
You're done. Chanu, can listen when you're done, give thumbs up. Yes, sir, done. Chanu, when you're done, give thumbs up. So we're done. So I start with something you are familiar with, radioactivity. Now, you see, I'm giving you K. First, I'm giving you K. Let's go the rate constant. Now, this is in A level only. We use this rate constant in radioactivity. Actually, in radioactivity chapter, K is called lambda. For the moment, I'll use K to avoid confusion. The different chapters, the K will be, this notation will be different. No? When it comes to capacitor, we use a slightly different notation. Later we'll come there, but it's a constant K. I'll call it K. It's called lambda. Other one different. So basically, for the moment, we will call it K. A, I'm giving, it's around 50 per second. So I want to find the half-life of this substance. So if I want to find the half-life of this substance, I know half-life of this substance is Ln2 divided by 50. Now I get it in seconds. How much is this? Ln2 divided by 50.
sir.
Yeah, what was well, Ln2 divided. Now I'm finding half-life. Half-life of this radioactive substance.
Sir, LN2, it has a value, sir?
Yeah, in the calculator, it has 0.693 or something. Just type in the calculator Ln2 or 50 and even external.
So where is it in the calculator?
LN button is there. There's a LN button in the calculator. Log on top of log or something. LN button is there.
Oh, got it, sir.
Somewhere there's a LN button in your calculator.
Sir, got it, sir. Yes, sir. Yes. So 0.0139.
0.013. Correct. That's answer. Correct. So that's the half-life. 0.0139 is the half-life of this radioactive substance. We'll try to find another one. I'm giving the K. K I am giving 0.016 per second. You have to find the half-life. It will be Ln2 divided by 0.016. How much is that? So now the chapter does not matter. Now, if it is capacitor, capacitor's half-life. If it is rate,
So
half.
43.32.
How much?
43.32.
40, right? 43.3. Okay. So now you can say it's general. It can be radioactivity, it can be rate of reaction half-life, or it can be capacitor half-life. Capacitor half-life.
So what does LN stand for, sir? Is it a month or something?
No, it's a log base. It's a special base of log. If it's a log, It's log 2.71 base. Log 2 base is there, log 3 base is there, log 4 base is there, log 10 base is there. No? Log 2.72. No? 2.72 base is called LN. It's a special base of log. That's why we call it LN. It's a base. It's a base of log. Now you don't like this, log. Log 2 base is there. Log 3 base is there. Log 10 base is there. So when the log base is 10, log base is 10, sometimes we write LG7. We don't write log, no, we say LG7. So similarly, when the log base is 2.72, it's difficult to write, no, we call it LG. It's a special base of log. We call it exponential E base.
Understood. So should we copy this down?
Yeah, copy this. Okay, so now this is relevant of the chapter. It can be radioactivity, it can be rate of reaction, it can be capacity, it can be half-life of a rate of reaction, it can be a radioactive substance half-life, If it can be capacitor's half-life, it's the same thing.
So 50 s to the power minus 1 means 50 per second.
Yeah, per second. Yeah, this will come always, rate constant will come per second. Whatever the chapter. It will come in per second. Half-life is a time, it will come in seconds.
So in this case, it's 50 per second. Is it?
Yeah, 50%. So half-life is a time, it will come in second. 1 hour,
So the half-life will be second.
second. It's a time, it will come in second. Like this, okay? Now, if this is per hour, this will come in hours. If this is per day, that will come in days.
So ln2 means like ln and to the power 2. Is it like we write the notation?
No, no, not two. Not like that. We write like this. Not power Ln. Parallel to that, you are write the two. That is Ln. No, no power. Ah, no, not like this. Huh? Don't write like that. Ln parallel to Ln in, we write a two there. That's how we write Ln. Not Ln two, Ln power two. Ln two. It's a number for you. Chemistry, physics purpose, it's just a number. Okay, after finish the thumbs up. We'll finish this off and stop.
So radioactivity is denoted by the sign lambda. Is it?
Huh?
The radioactivity is denoted by lambda.
Ah, no, radioactive chapter, when it comes to the chapter, I'll tell you what is this K stand. K is the lambda step.
Should we write it here or not?
No, no, no. If you want, you can write lambda. In radioactive, actually, this is called lambda.
So the wavelength one is it?
What?
The wavelength.
Wavelength notation lambda is same. It's a Greek alphabet, so you can use it in different ways.
The wavelength is written like this. Is it?
The wavelength is capital V. No, it does not matter. It does not matter. Wavelength is capital lambda. This is simple lambda. There is no difference here. So,
So can we write it like this?
hey, you write anyway you like. It does not matter. They'll understand something similar. Okay, then. Okay, now done. Then now go to now you know how to find half life. Suppose you found the half life. Suppose you found the half life. Then now they say, I will go with radioactive chapter, radioactive. I know T half life of a substance is, we say 20, 30 seconds. T half life of substance is 30 seconds. It has initial activity. Of is the 60,000 meters. The activity, final activity, 125 meters. How long it took? Are they asking how long it took from here to here? The time. Now this is little bit O level sum. O level also we can do it by, we know 1000. Chemistry also mostly you get sums like this. No? 1000 to 500. It will take 30 seconds. 500, 250, it will take another 30 seconds.
So it's 90.
96, 125. It will take 30 seconds. Okay. But the issue is this method won't work if I say 100. You can't, this is not a linear relationship. Getting it? Now for this it will work. Now my answer will be what? 90 seconds. We have done this sum in all. How long it will take? Time is 90 seconds. Is this part is clear?
Yes, sir.
The other two, Chanukya and Lisa understood this is the O-level normal half-life calculation. If the initial activity is 1000, how? Because every 30 seconds it will become half. 1000, after 30 seconds 500, after 30 seconds 250, after another 30 seconds 125. Chanukya, are you okay? This is the O-level way of doing this. But this won't work when there is 100. That's why we are giving equation now in A-level. Now, mostly chemistry, they can give something like that. Rarely they can give the other one. Normally, when they give the other one, they must give the equation. But like this one, there's a trick in the sum. There's a trick in the sum. You don't see the trick. But if you use the equation and get it, they have to give the marks. Okay, then that's why I'm teaching you now we have A. I give you the equation A naught e to the power, I said minus kt. Okay. So unit 6 also we are handling e to the powers. Now I just substitute. Now I am doing it with the equation, either the equation. I know this is the initial activity. I know final activity is 125. Initial activity is 1000. So I get e to the power minus, I need the k value here. I forgot to, we'll find the k value for this one. K value is
The
reverse.
K value,
The k value also I get to find. That's this way is difficult. Huh? The A level way is difficult to do the sum, but we'll do it and see now. For the sum like this, O level way is very easy. How to find the k for this sum? I know t half is equal to ln2 divided by k. First we'll find the k. K is equal to ln2 divided by t half. So how much is the k? Give me the value of
0.0231.
0.0.
231.
0.0231. I just check that whether this is correct or the percent. Every percent. 0.0.
The K value, it is radioactivity. Is it?
0.8 per second. 0.0231 per second. It's per second. Percent. Okay, now I'll write the equation. A is equal to A naught e to the power minus K2. Therefore, now the activity is 125. Initial activity is 1000 e to the power minus K2. Okay, now I'll make e to the power minus K2 subject. This divided by that 0.125. Okay, this is something new for you. You might be knowing this. E goes to the other side. E, when I move to the other side, it will become Ln. Huh? Inverse of E is Ln. So this, when it move to this side, it like sine goes to other side, sine inverse, it will become Ln 0.125. So my answer will be, my T is equal to Ln 0.125 divided by minus this 0.023. So can't see, no? I do it on top.
Excuse me, sir.
Yes, yes.
So the K value is not the half-life. What is the K value?
K value is the rate, no?
Okay.
K value is the rate. Okay, K value is not the half life. K value is rate. Okay, then I can see T is equal to Ln 0.125 should be divided by what? Minus 30. See, you get a T near to 90. Check it. How much is coming? It's near to 90. But you can see them. O level way is easier for this sum. But there are some sums we can't use the O level way. That's why we are teaching this method.
0.0693.
You can't, it should be 90. That was somewhere.
So I wrote Ln open bracket 0.125 close bracket divided by minus 30.
Minus 30. Others also check. This 30 is correct. Ln 2 over 30. Others check whether this answer is correct. 0.0231. Correct. Okay. Then what's the answer for this? Ln 0.125. No? 125 divided by 1000. Yes. How much is this? K is not minus 30. So, not minus 30 value. Minus 30. K is, sorry, I put the wrong value. Minus
K is 0.0231.
2. Sorry. K is not. Half-life is 30. It should be around 90.
So 90.
90, no? Okay.
Yes.
So copy
So
it.
what does the E stand for, sir, in that
E is
equation?
for,
The E.
E is now pi, like this. So the pi is 3.14. It's good continue. It's irrational. The E also something called 2.716, something like. It's a number, special number in science. The pi is a special number in science. It's a number. Okay, so E is also a number. That's what I said, 2.7.
The ln2 is also like a special constant, like a number.
No, not ln. ln2 is a number. ln is a special base of log.
So you can just say it as a constant, is it?
ln2 is a constant. Yes. So copy this. Now you can see it's of course when I do this O level sum in the A level, it's difficult. But O level, there's a problem. What's the problem in O level? If I say 100, this arrow diagram I can't find. But
So
in this case, it's
it's not
not
in a pattern, sir.
pattern because it's not a linear pattern. It's a curve. No? Otherwise, we have to get it from the curve. If we have a sketch, we can get it from the sketch.
So should we write radioactivity as the
Or
hospitality
radiative,
and
right?
just
Yeah,
write?
right, radiative. It's fine. We did for the radioactivity. Yeah.
So can we use that in chemistry as well? This whole sum we did similarly in chemistry.
Yeah, no, chemistry sum we are going to use it. The chemistry sums we can use, radioactive sums we can use, capacitor sums we can use. So there are 3 chapters we can use this equation.
The A node is the
Initial
initial.
initial value. If it is the rate, initial rate, A is the final rate.
So the goal, that one and other one has to be capital A.
Here. In this case, the initial activity, final activity. Same for, but when it comes to capacitors, it's initial current and final current. That's also like a rate, no speed, no current is rate of flow charge. These things most of the chemistry teachers don't do. They'll get a heart attack in this part. They are not that familiar with this advanced math. They skip this part mostly.
So which one, sir?
No, this is what I'm doing now. They skip this part mostly. And you see it in a paper, you also don't know. Amongst those one, they also don't know. They'll also do the way that teacher said, then you'll continue. But the chemistry teacher skip this part. The reason is that it's little advanced.
So this is in higher studies, sir.
No, not high study. Now, in the papers, the sum is there. But now if you don't know a technique, you do something, once in a while, the sum is there in the paper. So when you see the sum, you can't, you do it the way you want. And you don't know there's a sum like that also. You can't identify it if you haven't done it. But physics, everyday sum. Physics, chemistry, these are everyday sums. Chemistry, it's here and there. When it appears also, you don't realize it. Okay, after finish copying your terms.
So should we write ln then the line 0.125 again line?
Yeah, so whatever on the board, copy it. Yes. What's on the board?
So the line which I drawn, that's like a bracket.
No, that's same mod. It's okay, it's okay. You don't need that. The reason is this ln cannot be negative. No? That's why we are writing mod. That's called mod function. No, no.
So is it required, sir?
Huh?
Is it required for the sum, sir?
Not compulsory. No, no, normally that's what it is. I'm teaching maths as well, so that I feel like I have to put it there. For chemistry or physics, if you don't put the mod, it's not an issue. Maths, you have to put that mod. So the ln cannot be negative. If you put a normal, without that, no, we are saying without bracket, we are writing ln 0.125, that's fine, no issue. Huh? That's fine. That's fine. In chemistry and physics, there's no issue with that.
So done.
Okay. Then I will go to this sum and we'll try to do it in both ways. Using the advanced or normally, okay, normally you will get this O-level version of the sum. This is also O-level version. Now what they are asking, information half-life. So they gave the rate, now we can find the half-life. They gave the rate, first we'll find the half-life, they gave the rate. So ln2 over rate is the half-life.
So,
Yes, correct.
so rate can normally have the unit of h to the power minus 1 also. Like normally we write mode,
Other
the
units also
decimated rate.
can. Other units also can. But here, now we can do the sums for this kind of k values only. You don't get the other units. That's why examiner designed that to make it like that. Correct. Yes, there's a 8 out. No, there's another integer there. 27726. Then we found that. Now actual next part, we don't need that. Without the advanced equation, we can do it.
So half-life second is it, sir?
Use the information question, half-life, we found. They're saying half-life is this. They're giving the half-life because otherwise we can't do the next part. No?
So seconds, the half-life is seconds.
Seconds, yes, seconds. They gave the half-life. No? Explain why we found the half-life. Now they are telling it's dropping from here to here. But can you see, we can use the arrow diagram, no? So we will get the, this concentration, he did not give me what's the initial concentration. They gave for this 100 centimeter cube. What's the initial concentration? Put 10 equals CV and find me the initial concentration. Initial concentration.
18 to the power minus 5, sir.
18 10 the power. Right.
Minus 5.
Okay, right answer. 18 10 the power. Okay, now it's dropping from 18 10 the power minus 5. It's dropping from 18 10 the power minus 5 to 2.5 in 10 the power minus 6. Can you see this is the initial concentration? Concentration is dropping. This is the initial concentration. This is the final concentration. Now don't jump into the advanced formula yet. Because this sum can be done in O-level format as well. The advanced formula also will work. Huh? So now what I have is 18 to the n to the power minus 5, 2. Drop into 2.5 into 10 to the power vector. Copy it down to the power minus 6. I know the half-life. Right? It's dropping from 18 10 to the power minus 5 to 2.5 in 10 to the power minus 6. Okay. We see whether it's a 2 to the power sum. If it's dropped by 4, 8, 16, we can do it with arrow diagram. So divide 8 into 10 to the power minus 5 by 2.5 into 10 to the power minus 6. How much is that?
So we have to get it in terms of ratio.
If it is a 4, 8, 16 or
32.
32, I can do it with arrow diagram. I
So
don't
32.
use the advanced formula.
32.
Huh?
So 32.
32. That's in 5 half-lives. No? We can get the answer like that, okay? Without drawing the arrow diagram. 32 means, did you understand? Now this is dropped by 32 times now. To drop by 32 times, how many arrows should be there? 5 arrows. Getting it? 5 times it should drop.
So the half-life is normally
No,
what's
this
this?
is equal to 5 half-life, huh? Not the half-life. I'm telling how many half-lives. How many times this should happen? 1, 2, 3, 4, 5 times. Getting it?
So how did we know it's 5 times?
Why? After one half-life, you say this is the initial. After one half-life, this will drop by half. No? After two half-life, half of that, no? This will drop to a quarter. Getting it? After one half-life, it will drop by half. After two half-life, it will drop by 104. After three half-life, it will drop by 108. Did you understand? No?
So then the 32 then like is there a
32 means 2
overall
to the power
half-life
5.
value which is new?
2 to the power 5. No? So it dropped by 5 times. It's dropping by 2 to the power no?
Okay, so I understand.
2 to the power 5. So that's mean this is
So
5 half.
it's like a order.
Yeah. Now, if you use the arrow diagram, it will take some time, but we can do it if you want. So this is 18 to 10 to the power minus 5. If I divide it by 2, how much? 4 into 10 to the power minus 5. Then you get what? Then you get 2 into 10 to the power minus 5. Then you get 1 into 10 to the power minus 5. 1 divided by 2, 0.5 into 10 to the power minus 5. 0.25 into 10 to the power minus 5. Can you see half 5 half less? This is 0.25 into 10 to the power minus 5. This way is easier. Did you get it?
So the arrows, number of arrows gives the amount of half-lives.
Amount of half life, but you don't have to row that. There is no mark for that. So straight away we can put what? 2 to the power 5, we know there it will take what? 5 half life to drop that initial concentration to this concentration. This way is easy.
So if we can get 32 as a multiple of like as a power of
2.
something like 3 or
Yeah, that's what.
then all.
It's 3 half life. That's correct. If it drop by a factor of 8, that's been 3 half life. If it drop by a factor of 4, it's 2 half life.
So in this case, drop by a factor of 2, is it?
Factor of 32. That's a 2 to the power factor of 32. That's 2 to the power 5, 5 half life. So I realize this is 5 half life.
So is there a capability to denote 32 as a power of something else rather than 2?
No, no, no. Any other power you can't. It's 2 to the power something you can do. Half life, no? Half life means becoming half, half, half. Okay? Otherwise, you have to use the advanced formula here. If this is difficult, we use the advanced formula. It will automatically come. You don't have to think. That's the advantage. Huh? Advanced formula, you don't have to think. This is the O-level way. No? O-level way, you have to think it and you have to check it close. Whether this is the power. Okay, now this is the O-level. Actually, A-level way will be easier for you. Easier. So 5 half-life. So I know the answer will be that half-life I got, it will be 5 times. So this is the O-level way. Copy this? This is doing some O-level.
Excuse me, sir.
Yes, yes.
So due to this, going by 2 and 2 again and again, that's why 2 here is the main number and power is
Yes, yes.
5.
Now this is the okay. This is correct. Now, since you are finding this is difficult, use the equation. Remember, either way you are memorizing the equation for the physics and maths. Sorry, physics. It's there in the back of the web. But when you do many sums, automatical now when we do capacitors and radioactivity, many sums will be doing now. So automatical that equation will go to the brain. That same equation you can use here if you find this way difficult. So,
So
copy.
both the equations is A equal A naught E minus
Yeah, now
KT
we are
and
going to use that. Yes. Okay. 5 half right. Okay, copy this. This is the order. Examine
good
don't
answer.
the method here, whether you do it this way or mentally also some students can do, we don't know. Some student will take the calculator and divide it by 2, he'll divide that 2, and he'll find how many times 2, we have divided to get 5. That method also correct. Getting it? You divide this by 2, divide by 2, divide by 2. How many times I have divide by 2 to get that? Another method. So after 5 times dividing it by 2, I get this. That's in 5 half life. Okay, Chanu can listen. Can you done your thumbs up? Now we'll use the advanced formula. Okay, now Okay. This will be easier for you. But there is alien part over there. I will get you something with this. So now I use A is equal to A naught e to the power minus K. So my A is this 2.5 into 10 to the power minus 6. A naught is 8 into 10 to the power minus 5. E to the power minus 2. So I know e to the power minus kt is equal to this divided by this 2.5 into 10 to the power minus 6 divided by 8 into 10 to the power minus 5. Divided by 2 or something. But I'll do it now. Then ln of this value 2.5 into 10 to the power minus 6, 8 into 10 to the power minus 5. I want to find. No, we did not finish off the sum earlier. How much is the answer? 5 half-life. 5 into what was the half-life earlier, but earlier sum we did not finish it.
The 2 into 2 to the power 5.
No, 2 something, 277. Half-life was 2.77 in 10 to the power 4. 2.7, so earlier part we finished up 10 to the power 4. Therefore, the time is 1.39 in 10 to the power 5 seconds. 1.39 in 10 to the power 5 seconds. That's the final answer for the earlier part. Now we are doing it like this. Now this should be divided by, what is this value? What is this value? 1 over 32, no, as fraction. I think this will become 1 over 32. ln 1 over 32 is equal to, no, sorry, e to the power minus it is 1 over 32.
So I got negative values.
This one can't be negative. How can it be negative?
The ln is
ln. Okay. So then now my answer will be t is equal to ln of this. ln 1 over 32 should be divided by k value. K value they gave in the sum. What's the k value? 2.5 in 10 to the power minus 5. K value is 2.5 into 10 to the power minus 5. How much is that?
Minus 130,620.
This one should be that.
So I get the value as negatives.
So, so here this is negative. So there's minus k. I forgot to put this is minus k, and then divide is minus k.
So minus, how did it become minus? Minus 2.
No, this is k. When it goes to other side, it will be minus k. E goes to the other side, ln. I skip a step here. Okay, that's what's confusing me. So what I get here is ln 1 over 32 is equal to minus k. We get it like that. Then we have divided by minus k. See whether you are getting that answer 1.39 into 10 to the power.
Yes, I got 1.39.
Okay, so now there are two methods. You have to pick the method you like. The reasons, the Euler method also there. This equation also there. Both ways.
So we can directly write the answer. We get like 1,300 like
Yeah,
that.
1.39 and 10 to the power 5. Yes. Okay. Okay, then we'll finish for the day. When you finish, give a thumbs up.
Done. Sir.
Done. Channel can listen when you're done, give a thumbs up. Okay.
So that is the A2 method.
This is the A2 equation method. Now, A2 also we can use the half-life method. This is chemistry now. Most of your chemistry teachers will do it like that. They won't use this. They'll get a headache with this or a heart attack with this. But okay, then we'll finish for the day. See you next time.
Thank you,
Good
sir.
night.
Have a nice day, sir. God bless you.
Goodbye. Goodbye.